to work. Okay, I'll mute and let Anne take over the stage.
Okay, so can I check that you can all hear me clearly and you can see my slides?
No, wait a second, we don't hear you properly yet.
So tell me if you'd like me to speak so that you can check.
I think now it's better.
Okay, and can you also see my slides okay?
Yes.
Okay, and I will just let's get everything working properly before we start. I've got the chat window up so I can keep an eye on anything on there. I can see on the side the view of the lecture theatre, so I can hopefully see anything going on there. So I think we're ready to start. Okay, so I'm going to spend the first few minutes sort of talking about what I'm going to cover during my lectures and how. This first slide has a general sort of overview of the science topics. I'm going to start with a brief introduction to cosmology. The second topic is going to be the observational evidence for dark matter, which is fairly obvious why we want to cover that during a school on dark matter. How the ways you detect dark matter often depend on how it's distributed. So the third topic we're going to look at, oops, and I'm just breaking my iPad for controlling slides, but I think I've now fixed that again. As Babette said, bear with us with technology things. So I'm then going to talk about how dark matter is distributed, in particular in the Milky Way galaxy. And then the final topic for my lectures is that we can learn about the properties of dark matter, i.e. what particle it is, again, from astrophysical and cosmological observations. Now, when I set out to write these lectures, I was trying to divide things up so that one section equaled one lecture, but actually physics can't be chopped into bits quite that evenly. And so these sections aren't going to fit neatly into lectures. And in particular, the first section, the brief introduction to cosmology, that will take up all of this first session of mine and then overspill into my second one later this afternoon, I expect. I'm not 100% sure about how the timing will work. I want to stop lots to give you an opportunity to ask questions. So possibly come the end of the week, there's going to be space for me to add more material. And if that is the case, then I'll ask you what you would be interested to hear more about. So moving on to sort of what I'm covering and why. So the aim is to give you the background knowledge of cosmology and astrophysics that's relevant to dark matter to help you understand the rest of the courses in the school, and also more generally the background knowledge that's useful for carrying out research in the field of dark matter. So 7.5 hours of lectures is quite a lot, but on the other hand, it's not a lot. So I'm going to give you at the start of each section a list of books, web pages, review papers that I suggest that if you want or need to know more about a particular topic, you can go to those sources to learn about them. The first lecture is very much review material, so there won't be a huge number of citations. Normally when I'm writing a paper, I try to get my referencing right, as in reference the people who were the first to do something. With the scope of topics I'm covering here, that really isn't feasible. So what I've tried to do is cite review papers because they're easier to understand than the original papers often, or I've cited particular papers that I'm aware of, but you should be aware that they're not necessarily the definitive papers on the topic. What I'm trying to do is give you starting points for you to then investigate more if it is something that's interesting or relevant to you. Now, the depth of how much I cover things is going to vary. Key things I'm going to try and go into in a fair bit of detail. However, there are other things that I'm just going to mention briefly so that they're things that it's useful to have heard about. And so if you hear those things being mentioned, you've now at least got a rough idea of what they are. And something to mention as well is some of the things I'm going to be covering, for instance, later in the week, numerical simulations of the distribution of dark matter. Those topics are going to be covered later on in the school in more detail. And if there's any contradiction between what I say and what the expert says, then of course you should trust what the expert says. And then I guess the final thing I want to say is that obviously lectures like this can't go into the same level of sort of depth and rigor as a sort of traditional lecture course, you know, that you've done as a student. And so I'm not going to be able to do everything from first principles. What I'm going to try to do is explain the key results and the sort of where they come from, but without grinding through all of the maths. So obviously, it's really unfortunate that I can't be there with you to interact in person, but I do still want to interact with you as much as I can. So please do ask questions. So what I'm planning to do is pause after every mini topic, say after every 5 to 10 minutes, to give you the opportunity to ask questions. If there's something more urgent, as in something I've said which really doesn't make sense to many people, then I understand the organisers have said to sort of highlight it to them in the room, and then they will stop me so the question can be asked. And then also if there's any questions between lectures, please do email me. My email address is just my name @nottingham.ac.uk. It was on the first of my slides. So I just want to emphasize that I really am keen to sort of take questions however we can do it in this sort of hybrid thing. And then finally, those of you that are there, lucky enough to be there in person, I hope you get a chance to enjoy the mountains. And that's a photo of me enjoying the mountains on a previous trip to CERN. So, any questions about logisticsy things or anything anyone wants to say before we get started properly? Okay, so this first section is going to be a brief introduction to cosmology to set the general background. Now, you're all going to have very different backgrounds. Some of you might be working in cosmology. Some of you might have done excellent lecture courses before. If that's the case, then this is just going to be a recap for you. People who don't fall into those categories, those of you who are new to cosmology, this is going to be a very rapid crash course. And so the topics we're going to move through, first we're going to look at the overall evolution of the universe. Then we're going to move on to its thermal history, i.e. how the contents of the universe change as it evolves and as its temperature drops. And we're going to look in particular at two particular processes that are relevant for dark matter, that is nucleosynthesis and the cosmic microwave background. We're then going to look at structure formation, i.e. how galaxies and large-scale structure in the universe form. I'm very briefly going to tell you about gravitational lensing and the different forms of it. And then finally, to wrap things up, we're going to look at a couple of topics that are less directly obvious to dark matter, but nonetheless are worth mentioning. And that's inflation, a period of accelerated expansion proposed to have happened in the very early universe, and then also type 1a supernovae that provide observational evidence for the accelerated expansion of the universe, and hence provide a crucial sort of cornerstone of the lambda CDM cosmological model. And so just to emphasize, to really do cosmology properly would take sort of probably 20 lectures. And if you were going to start from first principles with general relativity, even more than that. So this really is just going to be an overview of the sort of the crucial results. So before we get started, here's the recommended further reading for this section. If you're not already aware, the Particle Data Group regularly release a sort of big review of particle physics made up of different topics. And it's often a really good place to go to sort of just learn the essentials of something. And there are 3 parts of that which are useful to this section. There's one on Big Bang cosmology, there's one on nucleosynthesis, and then there's one on the cosmic microwave background. In terms of textbooks and lecture notes, my favourite undergraduate or bachelor's level textbook is one called Introduction to Cosmology by Barbara Ryden. A lot of what I'm going to say, I'm going to try and follow her notation and approach. If you would like to go into more detail and depth, then David Tong at the University of Cambridge has some absolutely fantastic lecture notes. Actually, he has them on all sorts of physics. I've no idea how he manages to do this, but the ones that are relevant are his lectures on cosmology. And that's the URL. So if you clicked on that link in a PDF or in the lecture notes, that would take you to his online lecture notes. And I highly recommend them. So if you'd like to know more about cosmology. So let's start with the evolution of the universe. And this is a particularly busy slide because we've got a lot in it. And within the evolution of the universe, we're going to start by looking at the key equations and quantities that sort of parameterize the expansion of the universe. And the single most important thing is this equation here, the Friedmann equation. And it tells us how the expansion of the universe via the Hubble parameter capital H depends on its contents and geometry. And so a key thing is the scale factor A, which parameterizes the expansion of the universe. It just tells us how much, by what factor the universe has expanded in any given time. So here and throughout, I'm going to use dots to denote differentials with respect to time. I'm also going to follow the sort of cosmological convention of setting the speed of light c equal to 1 so that mass and energy are essentially equivalent. Another cosmological convention is to use subscript zeros to indicate values of quantities at the present day. It isn't used always. We'll see later on today times when it isn't used, but sometimes it is. And in particular, A0, the value of the scale factor today, is often but not always normalized to 1. So having said all that, let's unpack the Friedmann equation a little bit more carefully. So A is the scale factor. H, the Hubble parameter, is A dot divided by A. So it's giving us the relative expansion rate of the universe. And then the Friedmann equation tells us how it's related to the energy density epsilon, the geometry of the universe via the curvature parameter k, and k is 0 for a flat universe, greater than 0 for a closed universe, and less than 0 for an open universe. And as we'll see later on today, probably, there's actually observational evidence that the real universe that we live in is very close to flat, i.e. k is very close to 0, and that's excellent. That makes a lot of things easier than they would otherwise be. And then finally, lambda here is the cosmological constant, the vacuum energy of empty space. So H0, that's called the Hubble constant. It's the value of the Hubble parameter today. And it's often written in this form here. So 100 little h kilometers per second per megaparsec. So there's a couple of things to unpack here. The first is the units. Overall, it's got units of inverse time. But it ends up getting written in this form so that if you have an object and you know it's a particular distance in megaparsecs away, you multiply that by the Hubble constant and you get the recession velocity in kilometers a second. So that's a practical thing for astronomers. The other thing, though, that's very relevant for us, though, is this little h. It parameterizes the uncertainty in the Hubble constant. And discussing details of measurements of the Hubble constant is way beyond the scope of these lectures, but I'll just mention very briefly, since it's one of the hottest topics in cosmology at the moment, there appears to be a discrepancy in the measurements of the Hubble constant from different types of measurement. So for instance, from Planck, i.e. measurements of the cosmic microwave background and other things at relatively early times, h is of order 0.68 with a relatively small error. Whereas more astronomical local measurements, looking at the recession speeds of nearby objects and building a distance ladder to get out to slightly more distant things, that method gives slightly larger values. And as you can see from these error bars, the distant difference between the values is bigger than the errors on them. So it looks like there's some sort of tension. And what the cause of this tension is, as I said, one of the hottest problems in cosmology. Is it due to systematic errors that haven't been taken into account in the measurements, or is it due to some new physics? So I've just mentioned that very briefly. So if somebody says sort of Hubble tension to you at some point, you've got some idea what it is if you didn't already. So any questions here before I move on? So some more things, and this is just going to be a sort of rapid tour through things that are relevant. So to solve the Friedmann equation, it turns out you need to know how the density of the things that make up the universe vary with time due to the expansion of the universe. And the fluid equation here at the top tells us that E dot equals minus 3h, well, it's epsilon, isn't it? Epsilon plus P, where epsilon is the energy density. The first term on the right-hand side simply comes from the fact that as something expands, the density has to go down. And then the second term comes from the fact that if the pressure is non-zero, essentially work is going to be done during the expansion. The universe is made of various different things that we know about, and so we have to group them together according to their properties. And this is done via the equation of state, which is the relationship between pressure P and energy density epsilon. And W, the equation of state parameter, is a different number for the different types of thing. So first up, we've got radiation, which is the relativistic particles, i.e. photons and light neutrinos. And radiation has pressure, which is a third energy density. Matter is everything non-relativistic, so things that are moving very slowly so they don't exert pressure. And that includes the normal baryonic matter that we're made of, plus also the dark matter. And because it's pressureless in this case, W equals 0. And then finally, for completeness, we could write a cosmological constant in terms of an equation of state. It would have W equals -1. And dark energy more generally is anything with an equation of state that is less than -1/3. It turns out that's what you need in order to be able to cause accelerated expansion of the universe. So as I've already alluded to, knowing what the geometry of the universe is very important. And there's a particular critical density that if the actual density is equal to that, then the geometry is flat. And if we go back to the Friedmann equation on the previous slide, to find out what the critical density is, you take the Friedmann equation, you set lambda and k equal to 0, and you see how consequently the energy density and h are related to each other. And so this is what you get as your expression for the critical density. And so you see it depends on the Hubble parameter, so it, like the Hubble parameter, is time dependent. The quantity that's actually useful and we'll be seeing an awful lot of later today is the density parameter, and that is the density relative to the critical density. And you can define that individually for the different components, radiation, matter, baryons, or you can define it as the total density. And it's the total density that's what determines whether the geometry is open, flat, or closed. So a few more useful concepts. Moving coordinates. It turns out to be useful to factor out the expansion of the universe sometimes. So moving coordinates, you can think of them as a grid of coordinates that are carried along with the expansion of the universe. So if you have, for instance, two galaxies that are only moving apart due to the expansion of the universe, their position in co-moving coordinates remains the same. And so the co-moving coordinates x are related to real physical ones with this factor of a, the scale factor, here. Another key thing in cosmology is the Friedmann-Lemaitre-Robertson-Walker metric. It describes the geometry of space-time. And we're going to use it briefly here to sort of get to a few key results for the behavior of photons. So ds squared is the space-time distance squared between two nearby points in space-time. dt squared is the difference in time, and then r, theta, and phi are co-moving spherical coordinates. And here we've got the geometry of the universe showing up in the curvature parameter k. So fortunately, things simplify very quickly. Photons travel on what are called null geodesics with ds squared equals 0. As we'll see later on, we can assume that the universe is very close to flat, so k equals 0. And then for simplicity, we can also consider photons traveling radially so that the angular terms d theta and d phi are both 0. So in this case, with a couple of lines of maths, what we end up with is that for photons, dr equals dt divided by the scale factor a. And with a little bit of work from here, and if you're interested in this, how exactly this works, check out one of the textbooks, you can derive redshift, the fact that the wavelength of light lambda grows proportional to the scale factor a as the universe expands. And this is useful because it allows us to write a relationship between the scale factor a and redshift z. And redshift is the thing that's actually measurable, for instance, from the sort of redshifts of spectral lines. In several places later on today, we're going to come across the concept of horizons, how far light, information, relativistic particles can travel in a given time. So to calculate this, you need to take dr, integrate it from, well, the Big Bang or whenever the particular time of relevance is up to whatever time you're interested in, and then multiply by the scale factor a to turn it from a co-moving distance into a physical one. As we'll see in a little bit, how a evolves with time t depends on what the universe is made of, but very roughly as a generic result, what you end up with is the inverse of the Hubble parameter and what exact constant appears in here depends on what the universe is made of. But the key result to take away is the horizon distance is roughly equal to the inverse of the Hubble parameter. So again, I'll just pause in case there are any questions so far.
Yes, one second. Try.
Okay. If the microphone doesn't work, no worries. I can email or...
No, try.
Can I talk now? Okay. I am wondering, are we able to put any constraints on the equation of state for dark energy?
We are indeed, and I will mention this very briefly later on today. The answer is it looks like it's very close to -1, but it's a good question and I'll mention it later.
Thanks.
Any other questions while we're stopped? So shall I continue? I promise I'll give you a proper answer to that later, but it's one that's best saved to later. Okay, so let's continue. So as I've already said, the universe is made out of lots of different things, but as we'll see in about 5 minutes, it actually turns out for large periods of its evolution, it's a good approximation to say it's dominated by just one thing. So it actually is very useful to have a look at the behavior of simple universes that are made of a single thing. We'll start with the easiest one, and that is a matter-dominated universe. So a universe that's dominated by baryons and dark matter that have 0 pressure. If you then put that into the fluid equation and solve it, what you find is the energy density is proportional to the scale factor a to the -3. However, this is a result we can see simply physically, and that's just that energy density is going to be inversely proportional to volume, and volume grows proportional to a cubed. So the net result is that the energy density goes down proportional to a to the -3. And if you were then to put that into the Friedmann equation, what you find is that a matter-dominated universe grows scale factor a proportional to t to the 2/3. cosmological constant dominated universe, then we end up with A dot proportional to A. And so we end up with exponential expansion. And as I've already mentioned, you could also describe the cosmological constant as a fluid with the equation of state with W equals -1. And I think I've already said what I've written here about dark energy, so we can move on to the next slide, which is radiation, which is really important because we very definitely know that in the standard model, photons and neutrinos exist. And because they're relativistic, they have pressure equals energy divided by 3. And in this case, the fluid equation tells us that the energy density is proportional to A to the -4. But again, this is a result we can understand physically. We've got that the number density drops proportional to A cubed again. And in this case, we've got an extra factor of A due to the energy of individual photons dropping proportional to A due to redshift. And again, you put this into the Friedmann equation and you find that a radiation dominated universe expands A proportional to T to the half. So a little bit more about the photons. They have a black body distribution given by this equation here. So this is the number of photons with frequency in a small frequency interval. T, capital T is the temperature, KB is the Boltzmann constant, and in this particular equation, little h is the Planck constant. And so here we see we've got a distribution of frequencies and hence energies with a peak at around 2.8 times the Boltzmann constant times temperature, and then a tail because of this exponential of high energy photons. And as we'll see when we come on to the thermal history of the universe later, this tail of high energy photons has some important consequences. And overall, if you integrate this distribution, you end up with a total energy density that is given by a constant alpha called the radiation constant times the temperature to the power of 4. And as a brief aside, you could also work out the number density of the photons, and it's absolutely huge. 4 times 10 to the 8 per cubic meter. Whereas if you average all over the universe today, the number of baryons per cubic meter is less than 1. The universe is a very empty place. So the reason I'm emphasizing this is that there's a huge number of photons for every baryon, and that has important consequences. Radiation isn't just photons, it's also light neutrinos. And there's a simple relationship between the energy density of the neutrinos and the energy density of the photons. It's 0.68. And this comes from the fact there are 3 species of light neutrino. The neutrinos are fermions rather than bosons. And when you integrate over the energy distribution, the result is it's different by a factor of 7/8. And then electrons and positrons annihilate at some point in the universe's history, and they produce photons and rise and increase the temperature and energy density of the photons, but they don't do the same for neutrinos. And this leads to this final factor, 4/11 to the 4/3. And so you put all of those 3 things together and you get this 0.68. So here I've stuck very much with the sort of simple model with the things we know about in, but as you'll hear from other lecturers, there's good reason to think there are lots more particles than we know of in the standard model. And so a general expression, which I'm telling you about because you might see it later, is that the energy density of radiation is given by this expression here, where we've got the T to the 4 that we've seen before. But the new thing here is this G star, and this is the total number of effectively massless degrees of freedom. So i.e. number of particles that act as radiation. And we already saw that the energy density of radiation is proportional to A to the -4. So putting these 2 things together, we get this relationship here. And so provided the number of relativistic degrees of freedom remains constant, A is inversely proportional to temperature, big T. And something that will prove useful later on when we come to look at nuclear synthesis, and also it's just a useful rule of thumb in general, is this relationship between time and temperature, which you can derive various ways, including from the Friedmann equation. And that is that when the time is about 1 second after the Big Bang, the temperature is about 1 MeV. And just to sort of, for the more experimentally minded, when cosmologists say temperature is so many MeV, what we really mean is the Boltzmann constant times the temperature is 1 MeV. So in general, the universe is made up of all the different things we've talked about. So you need to take that into account, and you can rewrite the Friedmann equation, which we saw back at the beginning of this section, in this form here. So this is the general expression for the expansion rate of the universe, written in terms of the Hubble constant, its value today. And then we've got the terms from radiation, matter, the curvature of the universe, and the cosmological constant. And as I've mentioned before, redshift is a more practical way of parameterizing the expansion of the universe than the scale factor. So that's what we've switched to using here. And then we're using the present day density parameters, i.e. the fraction of the critical density that radiation makes up today and that matter makes up today. And then you can equivalently define density parameters for the curvature K and the cosmological constant lambda using these expressions here. And then hence you can do the same thing with the present day density parameters in this expression. And so the idea here is that observations will measure H0 and these present day density parameters. And then if you need to know how the expansion rate of the universe varies with time, you can get a computer to solve the resulting equation for you. And as I've already mentioned, fortunately, the geometry of the universe is very close to flat. So this curvature term is very small and can be neglected. So I've ordered these in terms of how rapidly they drop, with radiation first, then matter, then the cosmological constant. So we can have a look at the overall evolution of the universe as in terms of how the log of the density varies with the log of the scale factor. So at early times, the universe is radiation dominated, but the radiation density drops off very quickly as this red line. And so at a point, it turns out roughly 0.05 mega years after the Big Bang, the radiation and matter densities are equal. And then after this, we get a period where the universe is matter dominated. Matter drops off as A cubed, whereas the cosmological constant lambda is constant. So if you wait a lot longer to about 10 gigayears after the Big Bang, matter and lambda become equal. And then after that, eventually going into the future, lambda dominates, or dark energy, or whatever it is that's behind the accelerated expansion of the universe that we'll talk about later, comes to dominate. And so in general, while we've got all of these things making up the universe, for large fractions of the evolution of the universe, for instance, back in this period right at the beginning, it's an excellent approximation that the universe is radiation dominated, and it's only the radiation that's important in terms of the expansion of the universe, at least. So next up, we're going to talk about the thermal history, but any questions on the evolution of the universe first? This is the important thing which sort of underpins all of cosmology. And I think I can see some hands.
Go for it.
Oh, thanks. Does the overall radiation density change if we're not assuming instantaneous neutrino decoupling?
Oh, and the answer to that is I don't know. It sort of sounds that you might be more of an expert on that than me. So I think the answer to that is I don't know. It's possible that that's the sort of thing that matters for detailed calculations, but not for the overall picture. Any other questions?
Like 3, but it's actually 3.443, something like that. And it changes something like at the scale of 10 to the minus 3. If you assume non-instantaneous neutrino decoupling, if you assume that neutrinos are not exactly massless.
Cool, thank you.
Yeah, I probably should have put in a disclaimer. The simple thing I've just showed you assumes that the neutrinos are completely massless and is, yeah, a simplification. Anything else?
I think we're okay.
Okay, so let's then move on to the thermal history of the universe. And first, we're going to look at Big Bang nucleosynthesis. And so that's the synthesis of the nuclei of the light elements, i.e. deuterium, helium-3 and helium-4 and lithium. And it sort of happens over a period of time, roughly seconds to minutes after the Big Bang. So this is sort of almost an entire field of research in itself. It requires complicated codes taking account of all sorts of nuclear reactions. And so obviously what I'm going to do is just give you a very sort of qualitative overview. So before nucleosynthesis, but after neutrons and protons have been formed, we've got protons and neutrons being kept in thermal equilibrium by weak interaction. So this is before about 1 second or equivalently 1 MeV. And so we've got these interactions going in both directions, keeping the neutrons and protons in thermal equilibrium. And at this time, the ratio of their relative number densities is given by this expression here with the exponential. So you've got the difference in their rest mass energies because we've set C equal to 1 on the top here, and then this essentially the temperature or thermal energy on the bottom. And so when the temperature is high enough to be bigger than the small difference in mass between the neutron and the proton, the neutron's slightly heavier, the number of neutrons and protons is roughly equal to each other. However, once the temperature's dropped and that's no longer true, because the neutrons are heavier, there ends up being less of them. So that just sets up a situation where there are slightly less neutrons than protons. Eventually, as the universe expands, the timescale on which these reactions occur becomes longer than the age of the universe. So they effectively cease. And that's a process called freeze out. And you'll also hear that terminology used in other contexts, for instance, the production of WIMPs. And so I've used FO to denote the temperature at which it occurs in this case, and it's about 0.8 MeV. And at that point, the ratio of neutrons to protons has dropped to about 0.2. So with the weak interactions having ceased, you start building up the nuclei of the light elements. So a proton and neutron come together to make deuterium. You can then add another proton to make helium-3. 2 deuteriums can combine to make helium-4, for instance. However, at this point, we've got this tail of high energy photons. And so they then come along and destroy any nuclei that you make. And that continues happening until the temperature drops to about 0.1 MeV. And so there's this window where nucleosynthesis is trying to happen, but it can't because of the high energy photons. And in this window of time, the free neutrons decay. A free neutron has a sort of lifetime of order minutes. And so the number of density of neutrons to protons drops from the 0.2 we had before to 0.18. And actually a sort of thing to mention here is that if the lifetime of the neutron was much shorter than it actually was, all of the neutrons would decay away in this window of time and there'd be none left to make any light elements. And so we wouldn't have a universe that we were capable of living in. So we should think ourselves lucky that actually the lifetime of the neutron is as long as it is. But anyway, back to nucleosynthesis. The most stable of the light elements is helium-4. So the majority of the neutrons end up in helium-4. You get trace amounts of the other light nuclei, and the remaining protons, eventually, when they combine with electrons to form atoms, they're just going to be hydrogen. So a proper calculation comes out with these results for the mass fractions, i.e. what fraction of the total amount of baryonic matter is in each of these things. So we've got most of it being hydrogen, a large amount of helium-4, and then trace amounts of deuterium, helium-3, and lithium. The expansion rate of the universe plays a key role in how these numbers work out, and the exact abundances depend on the photon to baryon ratio. We know the photon number density because we can measure the temperature of the cosmic microwave background radiation, and I'll say more about that later on. And so hence, by measuring these abundances, you can measure the total amount of baryons in the universe. Now, in general, I'm saving talking about evidence for dark matter until the second section, but this is a case where we can finish this up quickly now, so let's do that. So this is a plot taken from the particle data group review, and it shows the abundances of the light elements: helium-4 in purple, deuterium in blue, helium-3 in red, and lithium-7 in green, as a function of the baryon to photon ratio, or equivalently the baryon density. And the thicknesses of these curves denote the uncertainties in the theoretical predictions, which come in particular from nuclear physics uncertainties. And so what you then want to do is compare these predictions with measurements of the primordial abundances of things. You can do this in various ways: helium-4 from metal-poor galaxies, lithium-7 from metal-poor stars, but the one that's most accurate is deuterium from the absorption of light from quasars as it passes through primordial gas clouds. And you can hopefully just see here the yellow box which comes from doing it. And that measurement you can then translate into a measurement of the baryon density parameter, and or equivalently the density of baryons. And what you end up with is that omega b, the baryon density parameter today, and in this case people usually drop the subscript 0, times little h, the dimensionless Hubble constant today, which is about 0.7, lies in this range here. So a couple of things to say at this point. We'll see later on that you can also measure the baryon density parameter from the cosmic microwave background, and it's possible to do it with much more accurately with much smaller error bars using the CMB, but the result you get is perfectly consistent with what you get from nucleosynthesis. And so here we've got two different ways of measuring something, completely different physics, completely different redshifts, but they end up giving us the same result. So that means we can be pretty confident that we're getting this right. The other thing I will mention briefly so that you're aware of it, and somebody eagle-eyed usually asks this question given this slide. Deuterium and helium-4 match up nicely, but it looks like there's this discrepancy between the observations of lithium-7 and what you would expect based on cosmology and the measurements of the other light elements. I don't know enough to comment on what the source of this is, whether it's nuclear physics, whether it's a systematic in the astronomy, or whether it's telling us there's some new exotic particle physics going on. But this discrepancy is what's called the cosmological lithium problem. But the thing that's important for us is that nucleosynthesis gives us a reliable measure of the baryon density, i.e. the amount of normal baryonic matter in the universe. So any questions about nucleosynthesis? So I can't see.
Yeah, go.
Any.
Yeah. On the previous slide, I don't understand the observations, these yellow boxes. Are they observing in that region, or what are they constraining something?
Right, so what they are doing is the different observations come out with measurements of the abundances of the particular light element. So, and this is one where my gesturing ability is limited electronically. So for instance, for helium-4, the measurement is coming out in this vertical region. And then the curve tells us what the corresponding range of baryon abundances is. So you translate this observational measurement on the y-axis into a measurement of the baryon density on the x-axis. Does that help?
But are you making measurements at different densities, or how do you make the measurement? I mean, is it like you have a set of, on the y-axis you have these values and you map them to the x values, or how does it actually work?
So, okay, so there's messy astronomical measurements of things going on here, but the bottom line that was what the astronomers can do is measure the primordial abundances of these light elements. So what they get to do is measure the quantity on the y-axis, i.e. the amount of the mass fraction of helium-4 or deuterium or lithium. And so that's given, so the y width of the boxes is coming from the observations. The theoretical curves tell you how we expect the measurements of the mass fractions to depend on the amount of baryons. And so it's those theoretical curves that allow us to translate an observational measurement of the primordial abundance, which is just a single number, into a measurement of the amount of baryons. So I think this one, if I'm still not managing to explain this clearly, could you perhaps shoot me an email and I'll have another go at doing it offline?
Yes, it's clear. Thank you.
So anything else before I go on? Right, so then on to the cosmic microwave background. So we'll look a bit more at this later on, either today or tomorrow. So this is just a sort of qualitative overview. So at high temperatures, the photons have energy that's greater than the ionization energy of hydrogen. So if you did get an atom forming, the photons would come along and kick the electrons out again. So the upshot is that at early times, we've got the universe being a ionized plasma of electrons, nuclei, and photons scattering off of each other lots. So the mean free path of the photons is very small. They can't travel very far. However, eventually, as the universe expands and cools, the energy of the photons drop and atoms can form. And this process is called recombination. And so this is the time and temperatures at which it happens here. And so again, this is something where the tail of high energy photons, or the fact that there's lots of photons for every baryon, comes into effect. This temperature is a little bit lower than you might naively expect based on the ionization energy of hydrogen, i.e. 13.6 eV, and then the mean energy of the individual photons. So once the universe then becomes neutral, shortly after that, the photons stop scattering and they just free stream through the universe. And so this is technically two separate processes, but they happen very close together. The stopping scattering is called decoupling, and last scattering is the last time they scatter. And so that happens slightly later on than recombination. So the recombination then causes decoupling. And so these photons free stream through the universe. They are the cosmic microwave background, or CMB for short. I haven't fact-checked this myself, but standard law is that the CMB is the most perfect black body, better than anything anyone has created in the lab. Here's a plot of intensity as a function of frequency, and the temperature is 2.7255 Kelvin with an absolutely tiny error bar on it. And so this I mentioned before is what allows us to calculate very accurately the energy density of the photons. So I'm going to talk a lot more about the temperature anisotropies later on in the next section. They're one of the most powerful tools we have in cosmology to determine the properties of the universe. In a moment, we're going to look at structure formation. And so the way that structure forms in the universe is initially the density is almost smooth, but not quite. There are small fluctuations. And then so gravity pulls things in where there's an overdensity, and then those overdense regions collapse to form galaxies, galaxy clusters, etc. And these initial small density perturbations also lead to anisotropies in the temperature of the CMB. So the temperature isn't exactly 2.72 Kelvin. There are slight differences in different directions. And these have been measured by a sequence of experiments, and the most recent of which is Planck and its last set of results. We've got a map here. So these are the temperature fluctuations on the sky projected down into 2D with the average temperature of 2.72 Kelvin subtracted out, and we're getting these fluctuations of order 10 to the minus 5. So they're sort of very small. And as we'll see in more detail later, the exact distribution of these fluctuations depends both on the initial primordial perturbations, how they grow with time, which depends on what the universe is made of, and then also the geometry of the universe comes in when you project length scales into angles when we look at the sky. But we'll look at this in more detail later. The way that it's sort of calculated is in terms of this thing called the angular power spectrum. So what you do is you take the temperature difference in a particular direction specified by theta and phi relative to the average temperature T bar. You take that fractional difference and you expand it in spherical harmonics. So this is the equivalent of doing Fourier analysis, but on the surface of a sphere in 2D. And then the angular power spectra CL is taking the coefficients of the expansion in spherical harmonics and sort of squaring them and averaging them. And large L corresponds to large angular distances averaging over every combination, and then small l is small angular differences. And so this then is the results from Planck. The data points with error bars are what Planck measured, and then the blue curve is a sort of simple lambda CDM model that fits the data excellently. So now let's have a look at, in a little bit more detail, about the sort of shape of this angular power spectrum. I see there's a question. Somebody's got their hand up. Yash Agarwal?
Yeah, so on the last slide, so when you're averaging over the angular power spectrum, sorry, do I keep my mic on or should I just type it? Should I just type the question?
It's probably easiest if you ask it.
You're fine. I screwed up, so go ahead.
Okay, yeah. So what's the average over in the angular power spectrum, the angle brackets?
So it's basically all the different possible combinations of regions that are a particular angle apart. And this is why you then end up with these bigger error bars at large L, because there are only so many combinations of regions that are a large angle apart. One thing I was about to say is I am absolutely not an expert on the cosmic microwave background. And later on today, I was going to recommend to everybody Wayne Hu's excellent website. If you really want to understand exactly the details of the cosmic microwave background, then his website is the best place to start. Okay, so then let's move on to why the curve has this shape. And again, later on, I'm going to show you some animations linking particular to the things we're interested in, the baryon density and the matter density. So this constant region at small l, or equivalently large angular scales, that's something called the Sachs-Wolf plateau. And in this region, the temperature variations are simply coming from variations in the gravitational potential. Very loosely, you can think of it as the photons having to climb out of potential wells. We then, moving on a bit, we get these sequence of oscillations, and these are the acoustic or Doppler peaks. And the physics of what's going on here is really very complicated, and Wayne Hu's website is the place to go. So what we've got is a photon baryon fluid. The photons are tightly coupled to the baryons and they're oscillating. Gravity is trying to pull things in, and pressure, due to the interactions between the photons and electrons, is trying to push things out again. So you've got these oscillations which are occurring in the potential wells that are generated by the density perturbations, essentially. And so regions are doing this, and they're being caught at different points in this oscillation. And so this first peak comes from a region that's just had time to go into a compression, and then rarefaction, compression, and so on. And so these peaks are coming from where you catch different length scales in the process of this oscillation. We'll come back to this later, and we'll see that the properties of these oscillations In particular, the heights of these peaks depend on the competitions that are going on between pressure and matter and potential wells, and they allow us to measure quite accurately the baryon and matter densities. And then the final thing, which is more clear on this log plot of the angular power spectrum, is that when you go out to large L or equivalently very small angular separations, we're getting to small regions of space, and this process of the photons decoupling, it doesn't happen suddenly. There's a region of time in which the photons diffuse around, and so you get what's called this silk damping tail, where the fluctuations are sort of erased on small scales. And I probably should have said at the beginning, on this plot, we've got the data from Planck in red, its predecessor WMAP in green. They were satellites that measured the CMB temperature isotropies over large scales. There's also been some ground-based experiments, ACT and SPT, which have been designed to measure the fluctuations on small angular scales incredibly accurately. And you can see their data points in sort of yellow and blue kicking in around L of 500, and then sort of coming down to large multiples here. So this is very technical, but it's one of those, I'll mention these things so you've hopefully got a rough idea. There are other things we get out of the CMB as well as the temperature fluctuations. And that's because the photons are polarized. And that polarization is usually analysed in terms of E and B modes. And there's a sort of direct analogy here deliberately with electromagnetism, that sort of E modes are the ones with divergence and the B modes are the ones with curl. And the E modes can come from Thomson scattering of the photons off of free charge particles. And so that's a physical process that's definitely there and it happens. The B modes can come from various things. For instance, the lensing of E modes as the photons travel towards us, scattering of the photons off of dust, or from primordial tensor modes. And I'm guessing that most of you are too young to remember this, but there was great fuss sometime in the past that BICEP 2 measured B modes, and the initial announcement was in terms that they'd detected primordial tensor modes, gravitational waves from inflation, lots of excitement. It turned out that what they'd actually measured was B modes from the things, the mundane astrophysical things that we know are there. And then finally, as I mentioned, the sort of photons get lensed as they come by the gravitational potentials. It smooths out the fluctuations in the acoustic peaks, but it turns out that this is a good thing. It gives us another handle for pinning down things more accurately. So what I showed you before, that is the temperature power spectrum, as in sort of temperature correlated with itself. Here at the top, we've got the cross correlation of temperature and E mode polarization, and that is now measured incredibly accurately by Planck. Also the power spectrum of E modes, and then the power spectrum of the lensing. And so you see these acoustic oscillations showing up there too. But I think from the point of view of an introduction to cosmology, the bottom line is that these quantities have been measured incredibly accurately and hence improved the ability of the CMB to measure the cosmological parameters. And we'll come on to that later on. So, any questions on the generalities of the CMB? It would probably be best if we save technical questions on the CMB until we come back to it either later this afternoon or tomorrow morning.
Yeah.
Just kind of a general question. So on the temperature power spectrum plot, does the fact that the low L observational data, does the fact that that doesn't match exactly the prediction potentially point to new physics?
So that is an excellent question. So this is not just a feature of the latest Planck data. This has been there for a long time, going back, I think, to WMAP. And when it first happened, there was an awful lot of theoretical work trying to understand this, and in particular, why this first data point here and its error bars lie below the curve. I must admit, I'm not sure what the current status of sort of the understanding of this is. Certainly people don't seem to worry about it anymore. And I think possibly the problem is when you've got one data point and it's an observation you can't repeat. And the fact is that L equals 2, it corresponds to sort of huge angular differences. So it could just be that things just got random weird rather than that there's something weird going on. But I must admit, I'm not 100% sure why theorists moved on from coming up with lots of models to explain this. If I've got time, I will try and look into this and report back in one of the later lectures. Anything else about the CMB?
Yeah, so could you just expand a bit on how temperature variations at low L are related to variations in the gravitational potential?
Without giving you an entire course on general relativity and Boltzmann equations, I'm afraid the answer is unfortunately not. But I will later today be showing you exactly what the equation is at least and talking through it a bit more qualitatively. So perhaps if we could save that one for later today, and hopefully what I'll say then might sort of fill in what you would like. But yeah, as I tried to emphasize at the beginning, given the sort of scope of things I need to cover and the hours I've got, it's not possible to do everything in great rigor from first principles. So what I'm trying to do is give a qualitative outline of how things work and then flag up sources that you can go away and look at the details if you want to. And anyone who's a theoretical physicist who's a fan of rigor, I realize that this is going to be unsatisfactory to you, but what I'm trying to do is sort of pitch things at a level so that they're maximally useful to everybody. So I sort of don't want to sort of confuse experimental physicists by throwing general relativity at them, because it's not necessary.
Could you just perhaps say like higher temperatures correspond to like higher potentials or like
well, as I just said, I will show you the equation later today when we come back to the temperature anisotropies. It's basically delta T over T is proportional to delta phi over phi, where phi is the potential. So anything else, or can we move on?
So what determines the max L you can probe?
Sorry, was the question, is there a limit on the L you can probe? Is that, am I understanding? So I don't honestly know. That's getting towards being an experimental problem that, you know, as in these things, CMB experiments tend to use sort of radio horns, and I'm guessing it's the experimental practicalities that sort of limit how small an angular difference you can measure. As you can see from this plot, though, the theoretical expectations are that the temperature fluctuations on average between small angular scales are tiny. So, and there's also, I don't think there's anything to be gained from measuring them. I think we really have mined all the information out of the CMB that we can. So then possibly the experimentalists could do better if they really wanted to, but I suspect this is one of those cases where the benefits of doing something better just don't justify trying to do it. Did that answer the question? Because I didn't quite hear the question. Okay. So very briefly, just to mention two other key events in the thermal history of the universe: the electroweak phase transition, when electromagnetism and the weak force decouple from each other. That happens at temperature of order 100 GeV. And then one which you might hear mentioned a bit in more detail, the QCD phase transition, happens before the things we've just talked about before nucleosynthesis at about 150 MeV. And this is the point at which there's a phase transition going from a quark gluon plasma into protons and neutrons. And this, I think, will have important things which come up in the lectures, for instance, on primordial black holes as a dark matter candidate. So those were just sort of setting those two events in the timeline of the universe. Right, so now on to structure formation. So I mentioned when talking about the cosmic microwave background that structures in the universe form via gravitational instability. We've got small initial perturbations and they grow with time. How those perturbations grow and then hence how galaxies cluster depends on what the universe is made of. So observing galaxy clustering is another way that we can measure the cosmological parameters, i.e. what the universe is made of. Now here and in subsequent slides, the figures I'm going to be showing you are old and out of date. That's not because I haven't been bothered to update them, but it's because as the field's got more and more technical, people have stopped making these nice figures that really illustrate the key physics. So the point I'm trying to emphasize is that these figures are here to emphasize the general principles, but that the details have improved immeasurably sort of in the sort of 10, 20 years since these figures were initially made. So on the left, we've got the results of something called the 2DF Galaxy Redshift Survey. It looked at two pie-shaped wedges of space and mapped out the positions or redshifts of all of the galaxies within them. And so we're in the center and you're going out to redshifts of order 0.2. And you can see that the sort of galaxies are clustering together. On the right, we have results from numerical simulations. And so I'll talk more about numerical simulations in the third section of the lectures. But very briefly, what you do is you create a toy universe in your computer made of particular things with a particular distribution for the initial fluctuations, and then you evolve it through time and compare it to the real universe. Again, there's been huge progress in simulations since this figure was made, but there's nothing out there that I can find, at least, that does such a nice job of summarizing the key results. So these are then slices through a 3D cube, color-coded according to the density. Yellow regions are high density, blue regions are empty space. The top two panels are for a universe just made of cold dark matter. And I'll tell you what the definition of this quantity sigma rate is in a moment, but it essentially measures the amplitude of the fluctuations on the scales corresponding to galaxy clusters. So 1.3 is bigger initial fluctuations. And so you can see if you increase the size of the initial fluctuations going from left to right, you're increasing the contrast. The denser regions are denser and the emptier regions are empty. Coming down to the bottom left, this is a universe with cold dark matter and a cosmological constant lambda. And as we've already seen, if lambda isn't zero, it comes to dominate the universe at late times and causes the expansion to accelerate. And so for the universe to expand exponentially. And so if the universe is expanding exponentially, that makes it harder for gravity to pull things together and for structure to form. So you see that in this case, there's relatively less structure and the voids in between are sort of larger and emptier than they were in the case of a universe just with cold dark matter and no cosmological constant. And then the bottom right, this is a mixture of cold and hot dark matter. And as I'll explain in a bit more detail in a moment, the hot dark matter, because it's relativistic, if you have an overdensity of hot dark matter, the particles can stream out of it, erasing the overdensity. And so small galaxies, they wouldn't form, and you get this sort of contrast. They sort of flood out into the voids. The contrast between the overdense regions and the voids is less than it would otherwise be. And I'll talk in a bit more detail about that in a moment, but that's qualitatively sort of how structure formation depends on the contents of the universe. So getting into now the technicalities of how these density perturbations evolve, the horizon, which I mentioned back at the beginning, plays a crucial role here. So perturbations are analysed into Fourier space in terms of their co-moving wave number k. So co-moving is with the expansion of the universe factored out. And when a given scale is larger than the horizon, i.e. regions that can be causally in causal contact, it can't evolve. Causality can't allow it to evolve. However, once it's smaller than the horizon, perturbations can evolve and they grow. So a key time is horizon entry, when the inverse of the co-moving wave number k to the -1 becomes equal to the co-moving horizon. So the horizon is h to the -1, and then we divide by the scale factor a to make it co-moving. So horizon entry is when those two things are equal. So it occurs when k is equal to ah. And that'll play an important role now in structure formation and later on when we come to look at inflation. So what I'm going to give you now is a very qualitative outline of how structure formation works at the level it's done by Barbara Ryden's textbook that I'd mentioned at the beginning. And it's really just trying to get a qualitative handle on how the physics works. If you would like a more rigorous analysis, then David Tong's lecture notes are the next place I'd advise you to go, or there's a sort of excellent textbook by Scott Doddleson if the details of this are really important to your research. So we'll start off with something simple called the gene instability. And we're going to, for simplicity, consider a pressureless static universe. So we're going to neglect the expansion of the universe to start with. And we're considering a sphere of matter that's overdense relative to the background density rho bar. So its density is rho, and the overdensity, the density perturbation, is delta. And you can derive an equation for how that overdensity behaves by considering the gravitational acceleration at the surface of our overdense sphere and taking into account that mass has to be conserved. And the result of that is the second derivative of the density perturbation is 4 pi g times the background density times delta. So that's an equation that's going to have solutions that are positive and negative exponentials with a particular dynamical time, which is constant in front of delta on the right hand of the side of the equation. So what we're seeing is that gravity is going to pull things in, and the density perturbation in our pressureless static universe would grow exponentially. However, pressure, if it's not zero, is going to resist collapse, but that takes a finite time, and that time it takes, t pre, is roughly equal to the radius of our spherical overdensity times the sound speed, i.e. the speed at which pressure can travel. And sound speed is the differential of the equation of state square rooted. So d pressure, d energy density. So it's square root of the W that we saw before. So for matter, that would be 0, but for radiation, it's non-zero. And so perturbations can only grow if this timescale, the pressure timescale, is longer than the dynamical timescale on which things can collapse. And so putting all the equations I've sort of got on this slide together, you end up with this relationship for something called the Jeans length, which is telling you the separation in a non-expanding universe between scales where perturbations can collapse and scales where perturbations are prevented from collapsing by pressure. In reality, of course, the universe is expanding, so you have to take this into account. And to do this, you can hand wave this using just Newtonian physics, but in reality, you have to use general relativity. You have to perturb the momentum, energy momentum tensor. It's a bit of a grind. So for the purposes of us, I'm just going to tell you the key results. So we're on sub-horizon scales. And so as I've already mentioned, perturbations on scales that are larger than the horizon at any time can't grow because of causality. On sub-horizon scales, though, we get this second order differential equation for the evolution of the density perturbation delta. And we unsurprisingly see that showing up in it are the Hubble parameter from the expansion rate of the universe and the matter density parameter, because obviously matter is what pulls things together. So as we previously saw, the universe starts off radiation dominated and then becomes matter dominated. So you need to solve the equation going through these two separate epochs. So radiation domination, the matter density is negligible. And as we saw before, the scale factor A grows proportional to T to the half. Putting those things into the differential equation, what you find is the following solution, i.e. a constant plus a logarithm. So during radiation domination, perturbations only grow very slowly, only logarithmically. And that's dark matter. We'll come on to baryons in a moment. On the other hand, during matter domination, when omega matter is 1 and A grows proportional to T to the 2/3, you get this solution with a positive and a negative power law. So once we get to matter domination, density perturbations in matter then start growing fairly rapidly as a power law in time. So what we're seeing here is that dark matter perturbations can grow significantly once we get to radiation matter equality, and then after that, when the universe becomes matter dominated. The baryons are different though, as we've already talked about. Before decoupling, the baryons and photons are tightly coupled together. So the baryons experience the pressure from the photons, and so they have a sound speed equal to 1/√3. And the upshot of that is that at early times, the baryon perturbations can't grow because the baryons are coupled to the photons. However, after decoupling, once the atoms are formed and the universe becomes neutral, the baryons decouple from the photons. And at this point, we've got potential wells that have been generated from the perturbations in the dark matter. And so the baryons then fall into those potential wells and sort of join the dark matter. And this is something that it turns out then leads to evidence for dark matter from just the amplitude of the CMB anisotropies, the fact that they're 10 to the -5. And that's something I'll come back to either this afternoon or tomorrow morning. So there's a difference in how cold dark matter and hot dark matter behave. Cold dark matter is particles that decouple when they're non-relativistic, and their velocity dispersion today is essentially 0. Hot dark matter is particles that decouple when they're relativistic, and the dispersion is not exactly 0 today. And so, as I've already mentioned, the hot dark matter has an effect on density perturbations. The hot dark matter becomes relativistic, non-relativistic when its thermal energy, 3 kb times the temperature, is roughly equal to its rest mass energy. And again, we set C equals 1 here. Before this, though, it's relativistic and it free streams, and it erases density fluctuations on length scales smaller than the time at that time. And with a detailed calculation, the result is this mass scale beneath which, if you have pure hot dark matter, it erases density perturbations, is about 10 to the 16 solar masses. And so for reference, that's roughly the scale of a galaxy cluster. So if we only had hot dark matter in the universe, it would erase the initial perturbations on galaxy scales, dwarf galaxies. And so the first objects that would form would be galaxy clusters. They would then fragment into smaller things. So what is said is that structure formation is top down, big things form first. Whereas, as we'll see in a moment, with cold dark matter, small things form first. As a very rough aside, because it might get mentioned later on, at very early times, the WIMPs can also free stream and erase perturbations too. But it actually happens on much smaller scales. So the corresponding scale beneath which perturbations are erased by cold dark matter, or at least for thermal relic cold dark matter like WIMPs, it's of order the Earth mass. So it's tiny for most practical purposes. So quantifying things a bit more, the quantity that's used for sort of parameterizing the density perturbations is the power spectrum. So we take our density perturbations in real space and we Fourier transform them. And then the power spectrum is just the average of those coefficients. And what we're often interested in is the power spectrum at some time t as a function of co-moving wave number k. And this can be written in this form So somebody's asking in the chat that there's a problem that they're not able to hear anything. Shall I just pause a second while we sort this out? Okay, somebody's saying they can hear. So, okay, I'll carry on at least. So there are two things here on the right-hand side. This capital T is the transfer function that describes the evolution of the density perturbations. And it comes from solving Boltzmann codes, which solve for the evolution of perturbations for universes made of different things. And then this curly P is the primordial power spectrum, which is generated we think perhaps by inflation, that I'll talk about later today. And this primordial power spectrum is usually assumed to have this simple form of a power law with amplitude AS. The spectral index NS describes the scale dependence of the primordial power spectrum. And then this K star is just a fiducial scale that you choose depending on what data you're interested in. And a Harrison-Zeldovich so-called spectrum corresponds to NS equals 1. And that's what's called scale invariant. If you then put NS equals 1 in here, what you end up with is a constant amplitude of the primordial perturbations on all scales. And this primordial power spectrum is something that can be measured from the Planck CMB data. So we've got that the amplitude is of order 10 to the minus 9. And so the amplitude of the perturbations themselves is roughly of order 10 to the minus 5. It's the square root. And interestingly enough, this spectral index of the scale of perturbations has been measured very accurately. It's 0.959 plus or minus 0.006. So it's close to this scale invariant value, but it's definitely not equal to 1. This difference, the difference is much bigger than the error. So we've got this thing where the power is bigger on large physical scales and slightly smaller on small physical scales. So just to sort of fill in some things that I've talked about. So a quantity that's useful is the mass variance, sigma, and it's essentially just the typical amplitude of the perturbations on some scale R, and it's calculated by taking the power spectrum, multiplying it by the Fourier transform of a window function, which is squared, which is what you use to select out the particular scale R that you're interested in, and then integrating over all co-moving wave numbers K. And so then that ends up giving you the typical amplitude of perturbations on some particular scale. And so sigma 8 is the mass variance on scales of 8, little h to the minus 1 megaparsecs, which corresponds roughly to galaxy clusters. And constraints that people make from large-scale structure observations, for instance, weak lensing, cluster counts, and redshift space distortions, which I'll say a little bit about probably tomorrow morning, they're often quantified in terms of capital S subscript 8, which is sigma 8, this mass variance, times the matter density parameter normalized to 0.3 to the power of 0.5. And it just turns out that practically that's the thing that they're most sensitive to. So that was an aside, so that if you see S8 mentioned somewhere, you hopefully know roughly what it is. Now I'm keeping one eye on time. We've got 5 minutes, but I think I should press on to the end of the structure formation section, and it might overspill by a minute or two, but not longer than that. And so a scale goes non-linear, i.e. the fluctuations become of order 1 and they collapse to form gravitationally bound objects once the mass variance is of order 1. So to give you a sort of visualization of this, on the left, I've got the power spectrum as a function of co-moving wave number. On the right, I've got the mass variance, which is probably the physically more intuitive quantity. Blue is for cold dark matter and red is for hot dark matter. And so the blue line is what you sort of expect just from the evolution of the primordial perturbations, but with hot dark matter, the free streaming of the density perturbations erases all the perturbations for large K or equivalently small length scales. On the right is the mass variance, and that then essentially grows with time. And as I previously said, structure formation starts when the mass variance becomes of order 1. So what we see with cold dark matter is that the mass variance is going to cross any given threshold soonest for smaller mass scales. So with cold dark matter, on average, small collapsed dark matter halos form first, and then larger ones form via mergers. Whereas with hot dark matter in red, this line is supposed to be exactly flat. So it's the 10 to the 16 solar mass galaxy clusters that would form first. And we know that that isn't how structure forms in the universe. It doesn't match observations at all. So we know that all of the dark matter can't be hot dark matter. And if you wanted to understand in more detail why this curve has this shape with a sharp power law here and this shallower slope here, the short answer to that is that the shallow slope here comes from the logarithmic growth of perturbations during radiation domination. And so these are these small scales that enter the horizon during radiation domination and then can grow logarithmically. Whereas the steeper power law comes from scales that enter the horizon after radiation matter equality and then can only grow logarithmically from there. The shape of the power spectrum depends mainly on, it turns out, the combination of the cold dark matter density parameter and one power of dimensionless Hubble constant. And the reason for that is what sets the horizon scale at radiation matter equality. And hence this is what sets this division between scales that can grow logarithmically for a little bit before growing steeply and scales that can only grow steeply. And so again, this is an old figure with old data in, but I couldn't find any more modern figures that showed this so clearly. So we've got theoretical predictions as the lines compared to the data points for a particular slightly different form of the power spectrum. And the solid lines going from bottom to top are changing the combination of omega matter times little h from 0.1 up to 0.3. And then in each case, we've got a dashed line with no baryons and a solid line for the amount of baryons that we are pretty sure there are in the universe from the results of Big Bang nucleosynthesis. And so what you see, if you sort of compare a pair of dashed lines without baryons with the corresponding solid line with baryons, is you've got an overall effect on the amplitude, and you've also got these oscillations. So to wrap up for this session, I will just talk very briefly about those oscillations in the power spectrum that show up if you've got baryons. So they are called baryon acoustic oscillations. And as we'll see in more detail, hopefully later this afternoon, the sound horizon at decoupling, i.e. the distance sound waves can travel prior to decoupling, is what sets the acoustic scale of the peaks we saw in the CMB. And that same sound horizon at decoupling also generates a standard ruler feature in the clustering of galaxies. And I'll say more about standard rulers later on. And so this is most simply, at least, visualized in terms of this correlation function zeta r, and it tells you how much the probability of finding two galaxies separated by a distance r is enhanced above what you'd expect if they were just scattered around randomly without any clustering. And so mathematically it has this form here where you're averaging over the overdensity at x plus x a distance r away for all possible combinations. And so again, it comes from sort of taking an integral in k space of the power spectrum. But what matters for us is the physical interpretation. And so these baryon acoustic oscillations, they're now a big tool in cosmology, and they were first measured in about 2005, which is when this figure dates from. So the pink line is what you expect for a universe with just matter and no baryons. So you just have this linearly decreasing correlation function. The green, blue, and red and blue lines are from the amount of baryons we think there are in the universe from nucleosynthesis, and then varying the matter density. And what you see is you get this bump in the correlation function from these baryon acoustic oscillations. And the height of that bump then depends on the matter density. So hence why this is a sort of useful tool for measuring the matter density. And we'll look at the results from that later. So the next thing I've got planned in general is looking at spherical collapse of individual halos, but now I think is a good time for us to stop for this session. So any questions on anything I've said so far today?
No questions here.
So apologies for the slight overrun. It's very hard to get the timing right doing this remotely. And yeah, I'll see everyone later today to sort of pick up from where we've left off doing our introduction to cosmology.
Awesome. Thank you for the great lecture.
Thank you.
Thank you.
Thank you.
So is it okay if we just